We can go live now.
Okay, good morning, good afternoon, good night, wherever you are, everybody. We are going to start the third day of the workshop. Before starting, I received many times one question. If I don't manage to finish all the tutorials today, can I still get the certificate? Yes. The workshop is intended to become an online course after we end, and it will be always there on Thinkific. We will upload all the video. We are working to add also the slides of the lectures. That's another question I got. So the course is still there on Thinkific in the platform where you register. So you can go there with your time, do the tutorial with your pace. As we explained you many times, you have some help in when you try to put the solution of the tutorial. So you can do with your time by yourself, and even after the workshop, you can still use ask.iguin.org to ask question if you have some doubt. Probably we will there will be a bit more delay in replies because we will not all be focused in the workshop after it ends, but still you can do it yourself even after. Okay, after just this as the introduction, now we can start the lectures of the third day. Today we will have two speakers. We will discuss again about the searches and about the way we do the parameter estimation. The first speaker, and again, I'm sorry if I mispronounce your name, is Soichiro Morisaki, who is a LIGO member of the University of Tokyo, and is working on parameter estimation for compact binary searches and also dark matter searches. And I leave you the floor, but okay, now I see the slides. So go on, and sorry, before you start, as usual, put your question in the channel, in the topic of Ask Iguin about the lecture number 3. I sent you the link yesterday. You should have it.
Hi, can you hear me? Sorry. Okay. Thank you for the introduction. And hi, everyone. Thank you for coming, joining the workshop today. Today, I'm going to, so I'm Soichiro Morisaki, working at the University of Tokyo. Today, I'm going to talk about the inference of the source parameters of compact binary crescent signal. So yesterday, we had a nice overview. Sorry, I have, okay, yep. Okay, so yesterday we had a nice overview from about the compact binary crescent search from the COSTA. And after the search finds signal, then the next important task is to interpret the signal and extract physical or astrophysical information from the signal. So in this talk, I'm going to talk about what information we can get from signal and how to do it. So this slide basically summarizes the problem we are considering here. From the observed signal, what we want to do is to infer the properties of the source, such as the masses of the colliding objects. So the right figure shows the probability distribution of the masses of colliding objects of GW 150914, which is the firstly discovered gravitational wave signal. So the horizontal axis shows the mass of the heavy object, which is denoted by M1. And the vertical axis shows the mass of the light object, which is denoted by M2. So the M1 is by definition larger than M2. So we only need to consider the lower light region in this panel. And here, this color intensity represents the probability value. and this contour encloses the region whose total probability is 90%. So basically, roughly speaking, this region, the true values of the masses are likely to be located at this region. So, sorry, and our goal here is to obtain this kind of probability distribution for all the parameters we can measure from gravitational wave data. So at the first of the talk, let me introduce what parameters we can measure from gravitational wave data. So first of all, as I introduced in the previous slide, we can measure the masses of colliding objects. So the right figure shows the signal starting from the 20 Hertz with different masses. So this symbol here, m dot, represents the mass of the sun. So the blue one signal is from the 35 solar mass, 25 solar mass binary, while the orange one comes from the 25 solar mass, 15 solar mass binary. And as you can see in this figure, because the heavier binary emits higher energy with gravitational waves, the signal from the heavier binary more quickly evolves toward the merger, and the signal gets shorter and has a higher amplitude. So observing this, how rapidly this signal frequency evolves, we can measure the masses of colliding objects. Doing some calculation, we can also show that the frequency evolution of the signal is predominantly determined by this mass combination, which is called Chern mass. So in a typical analysis, for typical signal, we can measure this Chern mass combination most precisely. In addition to the masses of colliding objects, the spin angular momenta of the colliding objects also affect the frequency evolution of the signal through the general relativistic effect. So, and we can show from the general relativity that the what predominantly determines the frequency evolution are the spin components in parallel with the orbital angular momentum. So that this movie, shows the binary evolution with 3 different spin configurations. The left figure is for in the left figure, spin angular momentum are aligned with orbital angular momentum. In the middle, spins are vanishing. In the right, the spins are completely anti-aligned with orbital angular momentum. And what we find in this movie is that the aligned spins slows down the binary evolution, while the anti-aligned spins accelerates the binary evolution. So you can see that the right binary is the first to merge, and then the next is the middle one to merge, and then final one is finally the left one is merged. So observing how rapidly this signal frequency evolves, we can also measure the spin components in parallel with the orbital angular momentum. In addition to the parallel spin components, we can also measure the spin components orthogonal to the orbital angular momentum, observing the amplitude and phase modulation of the signal. So the reason why is if the spins are not misaligned with the orbital angular momentum, then that misaligned components causes the orbital plane to precess, and you see the you see that the orbital angular momentum slowly changing its direction with time, and reflecting this slow modulation. You can see in the bottom figure that the amplitude and the phase of the signal slowly modulates. So observing this amplitude and phase modulation, you can also measure the orthogonal spin components. And using those observations, we can measure masses and some components of the spins. And those are the key information to prove the formation history of merging binaries, because they reflect how binaries are formed in the universe. Okay, and in addition to masses and the spins, if the binary contains a neutron star, then the neutron star is tidally deformed by the companion star like this, so tidally deformed. And this tidal deformation also affects the frequency evolution of the signal. So this right figure shows the signal with and without this tidal effect. So as you can see in this figure, this tidal deformation accelerates the rate in spiral motion of the binary and makes the signal slightly shorter, okay? And this tidal effect, the significance of this tidal effect is actually dependent on the so-called tidal deformability parameter lambda. So observing this tidal effect, you can measure the tidal deformability parameter lambda of this neutron star. Since this tidal deformability parameter depends on the properties of the highly dense matter composing the neutron star, using this observation, you can also constrain the properties of the highly dense matter, which has not been fully understood by the previous experiments. In addition to those parameters, it is also important to measure the direction, source rotation, and it is especially important for the follow-up electromagnetic observations, follow-up electromagnetic observers. And we can measure that the direction to the source using the data from multiple detectors. So the idea is, if we have a multiple detectors at those locations, and suppose that gravitational waves are coming from this direction, then this gravitational waves first hits this detector, then next this detector, and then hit this detector. So we see arrival time differences dependent on the source direction, and using this information, you can constrain the source. Direction. We can also use the signal amplitude at multiple detectors, because the sensitivity of the detector is also dependent on the source direction. So using the different observed signal amplitude at multiple detectors, we can also constrain the source direction. And combining those information, we can obtain the this kind of two-dimensional probability distribution of the source location. And this information is especially crucial for the follow-up observers to determine where they point their telescopes. Okay, so to summarize, this is a standard list of the parameters characterizing the gravitational compact binary crescent signal. So we have, as I explained, we have masses, spins, tidal deformabilities, and source rotation parameterized by light ascension and declination. In addition to those parameters, we have also coalescence time, distance to the source, and some angle parameters characterizing the geometrical configuration. So in total, we have 15 parameters for binary black hole and 1 additional tidal parameter per neutron star. So there we have a lot of parameters. And I would also like to note that in the actual analysis, we use different parameterizations for masses, spins, and light ascension declination and coalescence time to improve the computational efficiency, but it is kind of a bit technical detail. Okay, so they are the parameters we can measure from gravitational wave data. And next, I will talk about how to infer them. So as I said, the information of the parameters are imprinted on the gravitational wave signal, plotted in red in this panel. However, as we learned from previous talks, the gravitational wave signal is typically tiny, and it is typically buried under the instrumental noise, which is plotted in blue in this panel. So to infer the parameters taking into account the noise uncertainties properly, we start from the data model that data is modeled as the sum of the CBC signal, denoted by H, and parameterized by the parameters theta and noise, which is denoted by N. Here, this parameters theta should be regarded as the vector of all the parameters characterizing the CBC signal. Okay, and for noise, we make the following two assumptions. One is that we assume that instrumental noise is a stationary process. So basically, we assume that the statistical properties of the noise do not change with time. And to be more concrete, we assume that the expectation value of the noise is constant with time, and the two-point correlation of the noise only depends on the difference time difference. And under these assumptions, it can be shown that the Fourier components of the noise actually have a nice properties. So to be more concrete, if you calculate the expectation value of the Fourier component of noise, then it is vanishing for the non-zero frequency component. So here, this FL represents the L's frequency being, and this large T represents the data duration. And more important thing is that if you calculate the correlation of the different frequency components, then you can, under these assumptions, you can show that they are vanishing. And this correlation is proportional to the Kronecker delta symbol. So you can simplify this correlation matrix using the Fourier transform. And here, this S is defined by the noise variance normalized by the observation time. And this S is referred to as the power spectral density, or PSD for short. And this quantity is useful to characterize the noise significance at that frequency. And the second assumption is that basically we assume that the noise follows the simple Gaussian distribution. And combining those two assumptions, we can show that the noise, each frequency component of noise follows the statistically independent Gaussian distribution like this. And this distribution is referred to as Whittle likelihood. And using this Whittle likelihood model, we can easily calculate our likelihood, which is the probability of obtaining data, assuming true parameter values data. So basically, we can start from this Whittle likelihood of the noise, and remembering that the data is the sum of the waveform H and noise N. We can reduce this N to the data minus waveform, and we obtain this likelihood form, this likelihood functional form. And observing this likelihood, you can immediately see that if the likelihood gets higher when this residual at the numerator gets smaller. So you can see that this likelihood basically quantifies how well the template waveform fits data. And so far, we only consider single data from a single detector, but we can easily generalize this likelihood functional form to the multiple detectors. So assuming that the instrumental noise from multiple detectors are statistically independent, we can show that the likelihood from multiple detector is just a product of the product of likelihood at each detector. So we obtain this form. And to compute this likelihood, of course, we need to calculate the power PSDS. And as you can see, because the PSD is basically the noise, the expectation value of the square of the noise, the straightforward way to estimate this is to take a lot of data sets which are away from the signal and just calculate their average. So the PSD estimated in this way using the data around the GW500914 is shown in the right figure. However, there is a drawback of this method so this method basically assumes that the noise spectra do not change over the data sets we are using for PSD estimation. And it could be biased if the noise spectra change with time. So to mitigate the biases caused by that kind of noise non-stationarity, there is another PSD estimation algorithm called the baseline algorithm, which basically fits the spectra of on-source data using some assumed functional form. And if you are interested in this baseline algorithm, you can refer to the Littenberg and the Cornish paper linked here. Okay, So now we can compute the likelihood of the of gravitational wave data. And on the other hand, as I said at the start of this presentation, what we really want to calculate is the probability of obtaining probability of parameter data. Because so on the other hand, the likelihood is the probability of obtaining data conditioned on theta. So we want to flip data and theta parameter theta here, and we use Bayes theorem for that. So what Bayes theorem tells us is that you can calculate the probability of obtaining parameter theta conditioned on theta by multiplying likelihood by the probability of obtaining parameter theta, and normalize it by the probability of obtaining data. And in this Bayesian inference framework, we call the probability of probability distribution in the left-hand side posterior probability distribution, and this probability of obtaining theta is called the prior probability distribution, and this normalized factor is called the evidence. Okay, and I will before moving to the next slide, I will slightly change the notation here to make this consistent with the notation in the tutorial notebooks. So from now, I'm going to use L for the likelihood, pi for prior distribution, and Z for the evidence. I'm also now writing explicitly write that those probability distribution are conditioned on the our hypothesis or model. For example, this hypothesis or model M can be regarded as the choice of the waveform model we use for the for calculating the template waveform H tilde. For example, we may want to use very simple waveform model based on the post-Newton approximation, or we may want to use a more accurate waveform based on the numerical relative distribution. And this kind of choice can be expressed by this hypothesis or model M. Okay. Now, to compute this Bayesian posterior distribution using this formula, we also need to specify this prior probability distribution. And in the typical gravitational wave inference, we typically determine this prior distribution based on our prior knowledge or belief on the parameters theta. For example, if we don't have any information about the parameters theta, then we can use the completely uninformative prior on them. For example, if we don't have any information about the source direction, then we can use the isotropic distribution on light ascension degradation. Or if we don't have any information about the masses, we can use a uniform in mass prior. On the other hand, if we have some information about the parameters, then we can easily incorporate that information in the prior. For example, if we know the if we know the source rotation from the electromagnetic observations, then we can use the delta function like prior centered on that rotation. While if we know the mass distribution from previous observations, then we can use that distribution as prior. On the other hand, this evidence is just a normalization factor of the probability distribution, and we don't need to compute it for inferring the source parameters. However, on the other hand, if we want to compare, if we have two different hypotheses or models we want to compare, then this evidence value is useful. For example, if we have two different hypotheses M1 and M2, then we compute the evidence values for two models and compare their values. And if we find that the evidence value is higher for model M1, then we can claim that M1 is favored by data and vice versa. Okay. So this is the basics of the posterior Bayesian inference. And now we know how to compute posterior distribution. However, unfortunately, it is still hard to extract astrophysical information from that because the posterior probability distribution is the function of many parameters. So as I explained in the previous slide, we at least have 15 parameters. And to extract the useful information on astrophysics, we need to reduce the distribution of that high dimension to the distribution of a few selected parameters we are interested in. So, for example, if you are interested in secondary mass M2, then we need to integrate this distribution over the parameters except for M2 to calculate the one-dimensional probability distribution like this. And or if we want to know the source direction, then we need to integrate this over the parameters except for light acceleration degradation to calculate the two-dimensional posterior distribution. And obviously, as you can see, that they require high-dimensional numerical integration, which is practically very difficult to do. But fortunately, we have a path forward here, and we can use the stochastic sampling algorithm to solve this problem. So the idea is, so rather than doing this high-dimensional numerical integration, we can generate the random samples following this posterior probability distribution and make their histogram. So for example, if you are interested in the secondary mass M2, then and if you have random samples following the posterior distribution, then we can read the M2 value from each sample and make the histogram of them like this to obtain the one-dimensional histogram. And in that way, we can easily make a distribution of whatever parameters we are interested in. This stochastic sampling method still requires the method to efficiently produce the posterior samples. But again, fortunately, we have several efficient algorithms for doing that. For example, the Markov chain Monte Carlo method or MCMC method is an efficient method for producing posterior samples and popular and widely used in various approximations. In addition to that, in gravitational wave application, we also often use the nested sampling algorithm, which is known to be robust algorithm for even if the posterior has a complex structure. Okay. And to give you a rough idea on how these sampling algorithms work, I will also introduce one of the simplest MC algorithms named Metropolis Hastings algorithms. So I will illustrate how this algorithm works with this two-dimensional simple Gaussian distribution. So here, those lines represent the contour lines of the distribution, and here is the peak of the Gaussian distribution. So this algorithm first starts from the randomly selected point, which is shown here. Then using the user-specified proposal distribution denoted by Q, it proposes a next point theta prime, which is denoted by theta prime randomly. Then this algorithm randomly accepts that proposal using with this probability shown here. And if this proposal is accepted, then this it jumps to this next point proposed by this proposal distribution. You can looking at this probability, the form of probability. You can see that this probability is proportional to the ratio of the probability of the next point and the probability of the current point. So the jump to the point which has a higher probability is more likely to accept it. So repeating this procedure, the point is rapidly moves toward the center of the distribution. So the light movie shows the thousands of points repeating this procedure, this acceptance and proposal and acceptance procedure. And interesting thing is that mathematics proves that the point repeating this procedure automatically converges to the sample following the posterior distribution. So due to this fact, so after enough number of iterations, these iterations, we can use those random points as the samples following posterior probability distribution. Okay, And I would also like to note that this is, again, the simplest algorithm of the stochastic sampling. And we have, there have been various more efficient algorithms developed in the last decades. To do this, we need a cause for that. But fortunately, we do not need to implement this algorithm from the scratch because there are various nice open source samplers. For example, for MCMC, we have EMCE codes, PTEMC library, and there are other libraries. For nested also for nested samplers, we have a dynasty library, which has been frequently used for the LIGO-BARGO Kagra analysis and other nested samplers. So if you have a distribution you want to you want to draw samples from, then you just need to install one of them and use it. Another good news is that you don't even need to implement gravitational wave likelihood prior from the scratch, because we have a open source user-friendly library named BBH for that. So this BBH has been extensively used for the previous LIGO-BARGO Kagra analysis. This library is written in Python, so it can be easily installed with pip and conda. And BBH already has all the necessary components for CBC parameter inference built in. For example, this library has a gravitational wave likelihood, frequently used priors, and useful parameter conversion functions. It also supports the open source samplers I presented in the previous slide, and it also has a native sampler named the BBH MCMC, so you can use whichever sampler you want to use in your inference. BBH is also not restricted to the CBC problem, and it can be used for analyzing the gravitational wave signal with general morphology, or it can also be used for simulating CBC signals as well as analyzing real data. And you will learn how to use this library using the tutorial notebooks we have prepared. Okay, so that's basically all for the basics of the gravitational wave inference. And I will very briefly, finally, I will very briefly introduce how to deal with the posterior samples produced by this produced in the gravitational wave inference. So if you want to work with the posterior samples posterior samples for the real signals we detected in the previous observing runs, you can download the posterior sample files from these links. And if you read these sample files, then you will find that the sample file actually contains this kind of spreadsheet where each column contains the samples for each parameter. And if you want to, for example, if you want to get the one-dimensional posterior distribution of one of the parameters, then you can just read one of the columns, and then you can just easily make the histogram using the Python code, using simple Python code. Or if you want to know the 90% credible interval, then you can easily calculate the fifth and 95th percentiles of the samples and draw the vertical lines there. Or using the popular Python module called Kona, you can also make the two-dimensional histogram of the samples, and it is especially useful for to understand the correlation of the multiple parameters. And you will learn more about reading and plotting the samples with the tutorial we have prepared. Okay, so basically that's it. So the conclusion, we can measure source parameters such as masses, spins, and tidal deformalities using gravitational wave data. And so this inference is typically performed with Bayesian inference framework, where likelihood is computed under the assumption of stationary Gaussian noise. And to tackle the high-dimensional problem, we generate random sample following this Bayesian probability distribution and make their histogram to estimate the source parameter values. And if you are interested in more details about it, you can refer to the BB document linked here, or nice review article written by Srein and Taro. So basically that's it. So thank you.
Thanks a lot, Soichiro. How is the correct pronunciation?
Yeah.
Soichiro. Oh, thanks a lot for this comprehensive lecture. I will read some of the question in the chat on ask.equin, but before I want to say one thing that is a question for you, but a general comment. So in this tutorial, when we ask the students to run some of the analysis, usually this analysis take few minutes. In some exercise, we ask to modify something, and in some case takes 10-20 minutes if you run on Colab. But how long it takes normally in the real case, the analysis to get the parameter estimation for one real event in our analysis? Rough estimate.
Yeah, so that's a good question. So it really depends on the signal duration. For binary black hole which has a short duration, then the analysis is computationally cheap, and it typically takes hours or at the longest day. But for the binary neutron signal which has a longer duration, then the analysis is more costly, and it can take months or even years. But so to solve this problem, there have been various techniques developed. For example, the techniques named the reduced order curvature, and using such kind of approximate methods, you can reduce the analysis time to hours or day for the binary neutron signal. Yeah.
Okay, so I asked just to stress that the exercise as a simplified version, but in the real case it takes longer, and it's not. So some students ask me, but don't we have a place where to run this to make it faster? No, because in it's also a problem for the collaboration, because it's a very complex method. Okay, so the last question that I see in the chat is, can you explain Bayesian inference in layman's terms?
Actually, I don't understand the question. What, Laymans Theorem? Sorry.
Yeah, it means in easy words, in very easy words.
Sorry, what you said? Laymans Theorem?
Yeah, it means in a very easy way, in very easy words for people that are non-expert.
So I think it's just explain it again in a simpler way.
Of the Bayesian inference?
Yes.
Basically, you mean the explanation of the Bayes theorem? Then, sorry if I don't know. I understand your question, but basically, so if you need an explanation of the Bayes theorem, then it's basically, the probability of probability of obtaining theta conditioned on data multiplied by the probability of obtaining data is basically the probability of obtaining theta, obtaining parameter theta and data. And you can also compute that probability in a different way. So we can compute that probability by multiplying the probability of obtaining data conditioned on theta and multiply it by the probability of obtaining theta, and using that equality and make move this probability of obtaining data to the denominator of the right hand side, then you can obtain this equality. Sorry, I don't know whether I understand your question, but
yeah, and I don't know. I'm reading what's written here. If the student that have asked, you can discuss in the chat after. And the same student asked if parameter estimation and noise reduction are related.
So typically, in the standard, it could be, we could, for example, we could do a simultaneous inference of the gravitational wave signal and some noise model to reduce the noise effects. But what we typically do in the LIGO-Virgo-Kaggle analysis is that before doing the parameter estimation, we work with the detector experts to first mitigate the noise in the data and then start the parameter estimation. So the noise reduction is completely a separate process from the parameter estimation.
Okay, so I think, okay, there is another question that was asked in different points, position. So how to generate the movie of the, that was shown earlier about the CBC. I think it was already, someone replied on ask.iguin, but
Yeah, so this is actually nice. This is from the nice work by the BJ on the. So you can just search for the binary black hole explorer, then you will have access to the bunch of the nice this kind of movies, and I think the codes to produce this movie. I'm not sure, but yeah, just Google this binary black hole explorer.
Okay, so I think we have more or less finished all the talking. So in the meanwhile, someone is asking if the meeting are recorded. Yes. So if you go in the GWOSC page, every day after we finish the lecture, I send an email to all the people registered. So if you have not received, it means that either you have not registered or you have not checked your email. So I've sent in these days, every day, a link to the recorded lecture every day. And also I put the link on the GWOSC page from which you register to this meeting. So, and also it has been added to the Thinkific. So it's in so many different places that you cannot miss the registration, the recordings. Okay. So I think we should close this talk now and go to the next speaker. Thank again Soichiro, and if there are remaining questions about this talk, continue on ask.iguin.org, and we ask the speaker to have a look at that. So the next speaker is Viola Sardini, who is a LIGO member, and she's working in Lyon. She's also a researcher on compact binary coalescence data analysis, and I leave her the floor. Thanks, Viola.
Yes. Hi, everybody. I hope you can hear me fine. We tested at the beginning in principle.
Yes.
So I'm very happy to talk to all of you here. Just to say that I'm connected from a study hub, so I'm in the same room with a handful of participants to this workshop in Lyon. Yeah, so I will try to talk about the science we do with these gravitational wave observations. And okay, I can change the slides. That's good. I guess on some introduction, I can be fast. According to Einstein's general relativity, gravitational waves are ripples in the space-time that propagate at the speed of light. And they cause the space itself to stretch in a direction while it's compressed on the other. What we'll try to see together is that those observations are very interesting because they allow us to probe gravity in unprecedented conditions. Indeed, although gravity is something we experience in our everyday life macroscopically, it is kind of hard to test it amongst the fundamental interactions. It is quite hard to test gravity in strong fields because it is actually very weak. And so gravitational waves are very interesting per se, because they inform us about gravity, but also we will see that they really are a new messenger from the universe. So our observations have many implications in different fields of physics. Okay, so there are many systems that can lose energy through gravitational waves. We try to search for many different signals. We typically divide the signals in two broad categories, the transient ones and the longer duration ones. So the transient ones are, for example, the gravitational wave signals that are emitted by a coalescence of two binary objects, or the ones emitted from a supernova explosion. And then longer duration signals are more, for example, gravitational wave emission from pulsars that are highly fastly rotating neutron stars, or what we call stochastic gravitational wave background, that is kind of a superposition of many unresolved sources that are too far away to be detected individually. So I just want to say, today I will really focus on the first category, so the compact binary coalescences signals, or CBC, an acronym that you've heard a lot. But really, I wanted to stress that the physics program of the International Gravitational Wave Detector Network is really wider than that. So we do cover many other searches. The reason why we focus on CBC today is that, I focus on CBC today, is that these are the events that we have observed until now. So what are these compact objects? The ones that we consider for our, because these are the ones that we can detect, as we discussed in the previous days, are neutron stars and black holes. Those are the remnant of a normal stellar evolution of a main sequence high mass star that, depending on its mass, will leave a neutron star or a black hole. So these are, a neutron star is mostly composed of neutrons, hence its name, with a crust of heavy nuclei and a hot plasma atmosphere. And then, depending on the theories, there might be some unknown exotic matter in its core. It is, just to tell you how compact this object is, you can imagine that a neutron star that would have a mass 1.4 higher than the sun, so 1.4 times the mass of the sun, typically we use the solar masses as a unit of measure, would have a radius of just 10 kilometers that you can compare with the, I don't know, 700,000 kilometers for the sun, for example. It means this is very dense, so just 1 teaspoon of a neutron star would weigh 100 million tons. Okay, so the neutrons are do not collapse gravitationally because of some nuclear forces and some neutron pressure, but when this system works up to a, let's say, limit mass, which is somewhere between 2 and 2.5 solar masses. When the mass is higher than that, there is a gravitational collapse. So all the matter collapses into a region of space-time with extremely intense gravitational field. That is what we call a black hole. So this is like a singularity in space-time. And it's called a black hole. It is black because neither matter or light can escape its gravitational attraction. And these objects, as we've seen already, they can have masses between somewhere around 5 times the mass of the sun, up to millions or billions of times the mass of the sun, for example, the black holes that are at the center of galaxies. So we will talk about binary systems today. So we consider binary systems with all the possible combination of these compact objects. So when I say binary system, is two objects that are orbiting around each other and then losing energy through gravitational waves and then merging. So we consider systems where I have 2 neutron stars, which we call binary neutron stars, so BNS. Then mixed system with a neutron star and a black hole, these are NSBHs, and then binary black hole system, so BBHs. You will see these acronyms a lot in the presentation. Okay, so to calculate the form, the shape of the gravitational wave signal that we expect to be emitted from the system, we assume general relativity. We have different techniques to calculate the signal depending on the phase of the in spiral. So you see this in the plot on the left. you have a small sketch. So you have a first phase that is called in spiral, where the two objects are far away. In that case, we have an analytic approximation for the waveform, which is basically a perturbation expansion in a small parameter, where the small parameter is v over c, so the speed of these objects divided by the speed of light. When the two objects get closer at the merger, we use numerical relativity, and then we use some perturbation theory to describe the ring down of these excited objects that is created. So in the plot in the center, you will recognize the amplitude spectral density. You're now expert about that. Again, this is describing the typical strain I will observe in my detectors just from noise as a function of the frequency. So the lower this is, the better, the more sensitive is my detector. And you have three color curves for three different signals. On the right, you also see the time evolution of the strain for these three signals. So the basic idea is that a signal must be higher than that for me to see it. And so the shape of the signal will really depend on the properties of the objects that were involved in the coalescence. So really broadly speaking, more massive systems will give gravitational wave signals with higher amplitude, but they will also enter our frequency, the band of frequency where we are sensitive for shorter time. So a more massive system will give a shorter signal in my detector and a higher amplitude. And the low mass system will give a longer signal, but a lower amplitude. And also for fixed masses and spins and everything, so the same signal, the amplitude of a signal decreases with the inverse of the distance. So not the inverse of the square of the distance. We're really sensitive to the amplitude and not to the power, which is something maybe a bit unusual. And it's good because we've seen that this amplitude is very small. Okay, so I have to discuss a couple of milestone observations. Let me first start with the first observation. This was in 2015, and it was really groundbreaking, the first BBH merger. And so this was a great success for both general relativity, but also for the LIGO experiments. You recognize here the plot of the strain in time, and then the frequency versus time plots. I don't think I have to stay long on this slide because you've actually played with this exact data during the tutorial. So I guess you're expert on that. A second milestone observation is the first observation of a coalescence of a binary neutron star system in 2017, and also the only, for the moment, gravitational wave detection with an electromagnetic counterpart. So this is GW17017. You see in the middle the signals in the three detectors. In 2017, Virgo had joined the run, and as described by Soichiro just before, our detectors are not sensitive to all the portions of the sky exactly in the same way, which means that having different detectors in different locations actually helps a lot in localizing the signal in the sky. This was the case for Virgo. So you see on the right, the sky localization. Light green is just LIGO, and dark green is LIGO plus Virgo. And of course, sky localization is super important if you want to tell astronomers, go look if you have an electromagnetic counterpart. So this was the birth of the multi-messenger astronomy with gravitational waves. Indeed, I'm not going through the details, but you see on the plot on the left, every line is a different, let's say, kind of observation or different wavelengths. And then you have written all the observatories that participated to the observation, and every colored bar is one given observation, and the x-axis is time. So you see the gravitational wave signal here, the gamma ray burst that was associated to the 2017 BNS, just 1.7 seconds later. And then you see that for seconds to hours to days, we've been observing the same actual astrophysical event with many, many messengers. So this was really very exciting for the scientific community. It allowed, for example, to study the process of a kilonova and to determine that this is what follows a BNS coalescence, and to study the nucleosynthesis in this kilonova, which gave us new insight on the creation of heavy elements in the universe. We will see later what else we've done with this event. So I will now focus on the latest results, which are from the latest observing run, which we called O3. It was in 2019, 2020. During this run, the searches for CBC signals were really done systematically. So it is cool that I'm the last speaker in this workshop, because now you actually know all the pieces of the puzzle. So you heard about the detectors from Victoria. So this produced H of T. You heard about data quality. During O3, the two LIGO and Virgo were included in the data taking. That's why I only have the example for 3, but you know, it is easy to imagine how this would be with 4 detectors, with Kagra as well. So you heard about data qualities from Ronaldo's. Then the CBC search pipelines will ingest this information, and you know, expert about match filtering, because you heard from Gustav, and you know that this naturally gives us this signal to noise ratio. Then the question we ask is, okay, given a candidate with a signal to noise ratio, how often I expect to get such a candidate just from noise? And the answer to this question is what we call the false alarm rate. And so this is what we use to determine if a candidate is significant. The false alarm rate, or FAR, is not actually the end of the story. If you open the catalogs, you will see another quantity that is called P astro. That's the probability of being of astrophysical origin. And I mean, we can discuss more in the questions, but just very broadly speaking, the FAR is mostly informed about the noise, while P astro also assumes a population for the signal. So that's a probability. It's between 0 and 1. It's also easier to read. Okay, so we have a list of our candidates, significant candidates. Then we take the time, the data around their GPS time, and we feed this to this very expensive Bayesian inference analysis that you've just heard about from Soichiro. And this will give us a set of posteriors, okay, for these candidates. And what we will talk about in my presentation is what we do with them. And we will see that together we will use them to understand gravity, astrophysics, nuclear physics, cosmology. Okay, so CBC detections have really become a routine of GW astronomy. So 2015, just one detection was like worth a Nobel Prize, and now we're kind of getting used to that, right? So this is the table of the detections that we had starting from 2015. And here the run 2019-2020 O3 run starts. So you have all these events. We now have around 90 significant detections. Well, you can look at the table, maybe zooming offline, but each square is an event, and then the rounds are telling you the masses and the nature of the objects. You also see how the detections have been accumulating as a function of on the x-axis, you have like a proxy for our sensitivity, and all of these events are from the latest run. So we typically collect all these events in our like flagship publications that are called Gravitational Waves Transient Catalogs, so GWTC. These contain a list of events with the significance and then contain the parameter estimation information. So you see here what a catalog abstract looks like. And these are exactly the same events that you find in the event portal that Eric described on Monday. So typically the catalog will contain some plots for posteriors. As you know, you can also download posteriors and play around with them. So you see here on the right, for example, one-dimensional posteriors for different observables, mass of the first and second object, mass ratio, effective spin, which is kind of mass-weighted spin, and then the luminosity distance. Every line is a signal. So a candidate is called GW for gravitational waves. Then you have the year, month, and day. And then you have the hours, minutes, and seconds in UTC. Here you have similarly the 90% confidence regions from the posteriors in two-dimensional planes. So effective spin versus chirp mass. This is a reduced mass, so here just introduced, and then mass ratio versus total mass. So you see how our events are distributed in the parameter space. You see, for example, we have much more at high mass. We mostly observe BBHs. We did have one additional BNS during O3, but 1904-25, unfortunately, with no electromagnetic counterpart, which is maybe not that surprising since this was a bit far away. Okay, so let me just some remarkable events from those. Typically, when we see events that are a bit special, we also have dedicated publications. So we've seen about BBH. BBH is starting from 2015. We've seen about a BNS detection in 2017, but actually we had to wait until 2020 to have our first observation of a mixed system, so NSBHs. So we started with 2 events in 2020. So you see here the sky maps and the dedicated publication. Then I have a couple of events I want to discuss in particular that also had specific publications. So let's look at this kind of plots, the masses in the stellar graveyard plots. So the y-axis is the mass, and the x-axis has no meaning. It's just to have some, room for plotting our events. So anything that is the green, the yellow points are neutron stars seen by electromagnetic means. The orange points are the neutron stars we see with LIGO and Virgo. And similar for the purple and blue points. These are black holes seen electromagnetically or gravitational wave or with gravitational waves. So you see that there is sort of a mass gap here. So there are not many objects observed between, 2.5 and 5. So this is something that we have seen already, that we have a maximum mass for neutron stars, which is around between 2 and 2.5 solar masses, but people typically expected not to have black holes below 5 solar masses, simply because we didn't observe any. And so we already see that our observations are kind of challenging our understanding of these astrophysical objects, because we have several objects that we observe that lie in this mass gap. So, for example, this GW190814 is a coalescence within a 23 solar mass black hole with a mystery object of 2.6 solar masses. You've actually just saw the posterior in Soichiro's talk. So this is like 2.6 plus or minus 0.1, right? So, so this is either the heaviest neutron star we've ever observed or the lightest black hole. Another event is GW190521. So I told you that black holes are like the remnant of a stellar evolution, but actually, from our understanding of supernova explosion, we cannot really produce 2 high mass black holes. So in this region, a supernova explosion would undergo a mechanism for which there won't be any black hole formation, but the star will be kind of blown away. So 190521 is the coalescence of 2 black holes of 66 and 85 solar masses. And it is not clear how we can create this by stellar evolution. So maybe these black holes are themselves the result of a coalescence, or they have been growing by accretion. So these are like interesting events. So we use this observation to do many things. Let me just go through a list. First of all, we can use them to understand gravity, as we said. Let me start with the waveform. I told you that we can calculate the waveforms assuming general relativity, but we also try to check if this assumption works. So what we do is, for example, we take our data and then we take our signals that assume general relativity, and then we subtract the signals from the data. So we subtract the signals that assume general relativity, and we look at what is left. And then we do some residual test, and we measure the coherent residual signal to noise ratio, coherent between different detectors. And if our signals really describe all the, if our waveform really describe all the signal that is in data, we should be left with something that is consistent with noise. This is what we test on the plot on the right. So in gray, you have what you expect from just noise, and in light green, what we observe. So you see that this is consistent. Another thing is that we do is here on the left, you have again the plot with the different phases. I told you that we have different techniques. So we redo our analysis, splitting our waveform in 2. We take just the in-spiral part, and then anything that is post-in-spiral. And then we analyze the event separately, and we determine twice, for example, the mass of the system. And then we go and check if the mass that we determine with the 2 halves of our waveform are consistent. And this is what you see in the plot in the middle. This is the fractional deviation, fractional difference of the mass and the spin, and you see that the difference is consistent with 0. We also, I told you that we have an analytical description for this in-spiral part, so we also allow in parameter estimation for some generic modification to the coefficients of this analytical expansion, and we find that all the possible variation are consistent with 0. Okay, so I told you that GW170817 was observed in coincidence with a gamma ray burst, which was observed within 1.7 seconds. So this allowed us, for example, to constrain the propagation of the speed of GW, so which is something that general relativity predicts to be the speed of light. And we could see that this is consistent with the speed of light within uncertainties. Also, we compare the luminosity distance of the galaxy where this BNS happened as measured from gravitational waves or from electromagnetic waves. So these two, let's say, simple measurement alone really put very strong constraints on alternative theories of gravity. So we are really starting to test things that were very hard to test before. So this was very important. Another thing that general relativity predicts is the effect of lensing, right? So lensing is, we do observe this for light. When light goes through a place where there's very strong gravitational field, it can be deflected. So you have here, you have images, example images of some deflection of lights due to lensing. And so we expect the gravitational waves can be lensed as well. So you have here, you know, a coalescence and then a strong gravity fields. And then, for example, you will see twice the image from an event. This is our interferometer. We didn't detect any lensed events, but we do search for them. And a detection would be, again, a test of general relativity. Okay, so we also use this observation to do some astrophysics. In particular, we've seen that we observe signals from astrophysical systems, so we can study the signals to understand better the population properties of these compact objects that are involved in our coalescences. Understand the populations means, for example, measuring the merger rates. So this is what you see on the table for BNS, NSBH, and BBH system. This number are rates, which means the number of coalescences that happen per unit volume, per unit time. Don't be confused by the many lines. It turns out that the rate depends on what we assume for the masses. But let's see, for example, the second line, PDB independent. What does 44 means for BNS? It means that if you take a sphere with a radius of 1 gigaparsec and you wait for 1 year, on average, you will have 44 binary neutron star coalescences in them. And similarly, in the same sphere, on average, you will have 22 BBHs. Which is kind of weird because I just told you that we mostly observe BBH signals. So this is maybe a question for you. So how comes that many more BNSs are produced, but I observe less of them? So maybe we can discuss later. Okay, we can also learn something about the mass of the objects that are in this binary system. For example, we did study the mass distribution of the few neutron stars we observe in binaries. We see that they are slightly heavier than the galactic neutron stars, and also they're not really peaked around the value. But as I told you, mainly we observe BBHs, so we mainly have new insight on the black hole population properties. In particular, you see on the right left, the structure, the posterior of the mass of the black holes. So we clearly see this distribution has a substructure. There is an accumulation around 35. Actually, from subsequent analysis, we also see other 1 or 2 accumulation around 10 and 18. So this is interesting. In this in the paper, the LBK consider different mass populations that you see a bit drawn here on the left. So this is interesting for people who study population. We don't have a clear understanding of this BAM, so we can have some theories, but it clearly informs us about the different formation processes. This is just for mass, but we also look at the spins, as you've seen. So we have evidence of spin precession, which hint to some dynamical formation. So how do this binary system form? And we also start to be able to follow the BBH evolution with redshift because we start to see a bit far away. And this is generally consistent with star formation rate. So most of our black holes might be of stellar origin, although we've seen, we think some of them might not be. So we have several formation processes. We can use this observation going on with the list to explore the extremely dense nuclear matter. So you see on the left, this is the phase diagram of hadronic matter, and you see temperature versus density, and you know that we do explore this diagram with many different, in many different laboratories on Earth, but it is very hard on Earth to test the very high density and low temperature. This is something for which neutron stars are actually invaluable laboratories. We would be unable to do this in a laboratory on Earth. And indeed, the neutron star nature will affect its behavior during the coalescence. So in the end, it will change the waveform that we would see in our detectors. So in particular, with gravitational wave, we can measure something that we call tidal deformability, so how stiff the neutron stars are. This is what we did with 170817. This is on the plot on the right. That's the color is giving you the posterior, and lambda is this famous tidal deformability. So that's the tidal deformability. It's just a number, it's dimensionless for the first and the second neutron star. And you see that we prefer smaller values, which means the neutron stars were very stiff. And all these lines with names, we don't go through the details, but are different models of neutron stars. So this one observation helped to constrain many models. So we have more compact neutron stars than what predicted by these, for example, two models up there. We can also use this observation to constrain cosmology. So you must be familiar with the Big Bang Theory, at least for the because of the TV show. The idea is that the universe is expanding. This is a bit shown in the drawing here. Imagine that the space is this surface of the sphere. This is expanding, so the distance between 2 points is expanding. The space really is expanding, and this expansion is faster for more faraway objects. So from Earth, if we look at something in the sky, we can measure its luminosity distance. This we measure, it's the distance that informs you about the reduction of the flux from a source. So if the universe was Euclidean and not expanding, this would be the distance, like the physical distance. But the universe is expanding, so the light that I receive from a source actually stretches, and gravitational waves too. And so we have a redshift. We can measure a redshift, which we call Z. So for close sources, the redshift and the luminosity distance are related by this law with this H0 parameter that is the famous Hubble constant. Wow, fire alert. Okay, it was quick. So this H0 describes the rate at which the universe is currently expanding, and it is, as you know, a very active, very actively pursued by cosmologists, because you see here it is mainly measured with in two different ways. You see here the history of the measurements in red and blue. And so lately, it looks like there is some tension in this between these two kind of measurements. And this is where gravitational waves can play a role, because we can help in constraining this H0 parameter. So I already told you that gravitational waves allow us to measure the luminosity distance. So if I have a way to measure the redshift of the galaxy, for example, where my BNS took place, I can constrain H0. So there are different methods to get the redshift. Let's start with the easy one. Imagine we have an EM counterpart. So I take the redshift from the galaxy information, that's an EM information, and I can measure H0. So this, unfortunately, as we said, only happened for the GW170817. And you see the plot that we produced on the right. So that's a plot from 2017 publication. In colored bars, you have the two measurements that are supposedly in tension, and in blue, the posterior we can get from gravitational waves. So this is consistent with everything, but again, it is just one event. But then what about all the BBHs that we observed, right? We try to be, smart. So we can do something even if we don't have an electromagnetic counterpart. So first of all, imagine my BBH is very well localized. I can go and look, I can open a galaxy catalog and look what galaxies are there, and maybe try to infer the redshift from there. Or also, you heard already yesterday that the masses we observe are actually affected by the redshift. So what we do is that we jointly constrain the cosmological parameters and the source population properties of the BBHs. So you see here again, this is on the x-axis, you have H0. In black, you have the curve that you've seen from 2017. And in blue, you have the new posterior we have when we combine the 2017 posterior with the best we could do with all the BBHs we observed meanwhile. Okay, so we can also use this observation to do some multi-messenger, what we call triggered searches. So this is searching for GW transient associated with some other observation. So we do this, for example, for gamma ray bursts, what we call GRBs, and fast radio bursts, FRBs. So the coalescences of compact objects involving a neutron star have been thought to be associated to gamma ray bursts for a long time. And I think we had a proof of that with 170817. For fast radio bursts, the emission mechanism is still unknown, but again, we think this might be related to coalescences of compact objects involving a neutron star. So if we have a detection, this could be a hint for their formation processes. For the moment, we don't observe any associated detection apart from 170817. So what we do is that we use the sensitivity that we determine on simulation to have some exclusion distance. This is what you have in the plots below. So this is something like, okay, I made my simulation, and if there was such a system here, a system that would give rise to a gravitational wave signal and the gamma ray burst at this distance, then I would have seen it. Since I don't see it, I can say that I exclude it, right? That this is more or less like how it works. And I have a final slide. We can also use the CBC techniques to search for, new physics, exotic compact objects. So we do that searching for hypothetical subsolar mass compact objects that are predicted by many models. So these would be compact objects with masses between 0.2 and 1 solar masses. And we can do that because we can use our classic CBC techniques. In our waveforms, we can put masses of 0.3, for example, and then we use the match filtering, as we know. For the moment, we have no observation. So again, we put limits on the merger rate based on simulation. So you see the limits here. This is on the x-axis, you have the mass of an object that can be subsolar, but goes up to standard masses. And then on the y-axis, an object that is only subsolar. And the numbers are the rates in gigaparsec -3 year -1 that we exclude at 90% confidence level. So these numbers are very important for people who work on model, for example, of primordial black holes or black holes created from dissipative dark matter. So they come with their theory model and they have to check their models against our observations. So we help them constrain their models. Okay, so I am at the end of my presentation. To conclude, our latest observing period was really a big success, and it is kind of a change of gear for our collaboration or international network. So the gravitational wave astronomy is really entering the era of statistics accumulation, at least for the CBC signals. We have, you've heard this many times, a new observation period starting in 1 week from today with better sensitivities and a longer run. So we will expect, I don't know, a factor 2 to 3 times the number of CBC observations. So that's very exciting. Already with the ones we had, which are about 90 high probability CBC candidates, we were able to put out many varied scientific results. Unfortunately, at the moment, we just have one with the electromagnetic counterpart. We hope we might have a new one, at least another one during the next observation period. But already what we have helps us to put constraints on sources, populations, and rates. It allows us to test general relativity and to do some cosmology study. And just a reminder, we do search for non-CBC GW signals. And although we have no evidence for the moment, we are getting better at that. So this could also be a surprise of the next observing period, maybe the first non-CBC observation. And as a general point, gravitational waves remain a newcomer among the universe messengers. So we still have room for unexpected, which is of course very exciting. So stay tuned. And I'm done with my presentation.
Yay, thanks. Thanks a lot, Viola. It was very nice talk. It's very nice to conclude with this positive message and with all this science. So I am also in a study hub. And I have a question here from a student. So I will start from a colleague, actually, not a student. So go on, Giacomo.
Hi, Viola. Thanks for the presentation. I have a question. So there was a few months ago a Nature paper, suggesting a possible association of the binary neutron star merger seen in O3 with a fast radio burst event I don't know if you have investigated that or if you have any comment on this event.
So I was not involved in any particular study. As I heard, this is a possibility. It is not, so within the collaboration, it is not clear that we are convinced by this association. But yeah, I guess what I can say is that this confirms that it is very interesting to look, for to do some triggered searches, because when we know about another event like a fast radio burst or a gamma ray burst, we can also use, I didn't discuss this here, but we can use some techniques that are a bit more sensitive than the usual just match filtering different detectors and then making coincidences. So yeah, I guess this adds to the interest of keeping doing these searches. But yeah, I don't have any special insight, but maybe, I don't know, someone else does here in the audience. I don't know.
Thanks. So I see other question in the chat of Zoom. Okay, so one question is for the BBH source redshift estimation, even for lowest volume localization, the number of galaxies would be larger. How do you identify the host galaxies then? Has this been done before?
Yes, no, you're right. And let me go back. So you're referring to this, what I said. Imagine we have, okay, we know we have some sky localization for our BBH. We don't have any electromagnetic counterpart. Also, we don't expect that from a BBH. Or, okay, it can depend on the surroundings of the system, but from an isolated binary black hole system, we don't. So I said, okay, maybe we can just open a galaxy catalog and go see what galaxies are there. And maybe this helps us to infer the redshift. And you're right. So first of all, this only works with very precisely localized events. And still, the galaxies can be many. Our catalogs can be not complete. So we had actually quite some studies of this kind of hierarchical Bayesian inference that we can do in these cases. What you can do is that you have some, for example, priors. For example, we think that is most likely that a BBH comes from galaxies that have a higher luminosity, for example. And it is proved that we can fold in this information in a Bayesian inference and get overall a correct result. I should add that, for example, if we take the O3, so we do study the systematics of this method. That's what I mean. But I should add that with the O3, this publication uses all events up to O3. And actually, I think this is really, really driven by the second method, the ones with population. So we only had, we had maybe one event that was localized well enough so that this first galaxy catalog method was really making a difference. But overall, what we do here is mostly constraining the IH0 with BBHs, so what we call dark sirens using population. But I mean, all your points are valid, and we try to, to take them into account and to have an understanding of the systematics.
Okay. So there are other questions. There are many questions. So I'm trying to disentangle. Yeah, but Viola, you don't see them because they send directly to me. That's what
okay.
So I'm trying to read them. So I think one one question that can be useful for in general the audience is what kind of non-CBC signals that are possible, and is it possible for us to search them in the available open data and through the techniques we learned here?
Okay, so the kind of, this is annoying. Okay, the kind of, okay, but just a drawing. We do search for many things. So you can search for, okay, that's the problem with CBCs. When you search for something very particular, you have seen with match filtering that that's a super powerful technique when you know exactly the waveform, but somehow if you search for something very particular, you only find what you're looking for, right? So people sometimes are worried, like imagine we have another signal, a different signal. It could be a supernova signal. It could also be a coalescence with objects that are, for example, orbits that are very eccentric. there might be some things that we would miss with our waveforms. And the thing is, the LDK would not miss them because we do look for other signals. So in the transient world, for example, looking for supernovae or any transient signal that we are not sure how to model, we have, for example, other searches. So this won't be the techniques discussed by Gustav yesterday, so the match filtering. These searches are more, they don't assume any model for the signal, but they basically look for some excess in the power in the data. So you can imagine, you've been looking at, it's kind of what you do with your eyes when you make Q-transform frequency versus time scans. So we do look at these scans and then we analyze them in tiles and we try to see if there is really some excess of power with respect to what we expect from noise. And so these are what we typically call burst searches. That can be, so they can be sensitive to some signals that would escape our match filtering. And by the way, burst searches did find many events during O3, but all of them were also found by CBC searches. So they work, and for the moment they don't add anything. But if tomorrow we have a supernova, we will miss it with match filtering because we don't have the waveform, and burst searches will hopefully see it. So that's for the transient. For the longer duration signals, for example, something that we might hope to see during O4, I don't know, it would be a first GW emission from a neutron star. So neutron stars, you remember that a system must be non-symmetric to emit gravitational waves. So this is kind of, sometimes we say, yeah, we are constraining how high are the mountains on a neutron star. So any non-symmetric feature on a neutron star would imply some gravitational wave emission. So this is something that people search for, and we are getting really good at that. So we are really hitting the sensitivity limits where we could see something. It, of course, depends on the structure of the neutron star. And these signals are very different from the ones we discussed. They would be typically emission at a given frequency related to the neutron star rotation frequency. And and they will be persistent. So these ones are not happening at some times, but they are signals that they get more and more significant while you accumulate data. So, and you should see a signal at a given frequency. So these are also, if you can imagine, it's all another world of detector understanding and noise hunting, because all these lines we have in our PSDs, typically they will annoy a lot these kind of searches. So I guess of course, you can do these searches on open data because you have the, you have H of T and the data quality information. But, I guess you can search for some example of open source codes, but it is true that the workshop, unless I see that we have a non-CBC example today, but okay, the workshop is mainly giving examples about CBC. But I mean, all the data is public, so yes, you can in principle.
Yes, so just to add, if you go in the guosc.org website, there is a section that is called software that collects all the open software that is available. And so, as Viola said, if you scroll there, you can look for some open example. But as you can imagine, for reason of space and needed to space from human in the sense of time needed to run and organize the workshop, is impossible to describe in detail all the other methods. So it's a choice to describe the one that have given the discoveries until now. Even if, as Viola said, the burst searches were actually the first detection was, I think,
Yes.
was a burst detection before then CBC detection. But it's also more complex to understand, so it's many reasons why we choose to discuss this mainly. Okay, so there are many other questions, but it's very late. So I suggest to those that have written directly to me in the chat to instead copy their question on ask.iguin.org in the appropriate topic that I've sent by email, and I copied at the beginning of the lecture in the chat. And we in the sense, me, the mentors, maybe Viola if she has time, we will have a look and reply offline to your question. So I think now it's the good moment to thanks again Viola and Soichiro, and in general all the speakers of the workshop. It has been a pleasure to have you and to hear all the discussion and everything that has happened. And now I leave the floor to Greg, who is another organizer of the workshop, who will guide us through the workshop, the tutorials of the last day.
That's wonderful. Can I just check? Can you hear me okay?
Yes.
That's enough. Excellent. Thank you so much. Let me also take this opportunity to thank Anita and Soichiro and Apratim for taking the brunt of the organization for these. As you can see, I'm in a cafe at the moment, unfortunately. So hopefully the sound is okay, but please let me know if something goes wrong. And it's on the way to our workshop here in London, so that's why I'm in a cafe. I don't usually take calls from cafes. Okay, yeah, so we had some really nice talks this morning from Soichiro and from Viola. And so the notebooks today are really focusing on, Soichiro told us about parameter estimation. So we have 3 notebooks for you today. The first is an introduction to parameter estimation. What this notebook is going to do is it's going to introduce in detail some of the ideas that Soichiro talked about, so stochastic sampling in particular. And in order for us to do that in a way that is sort of fast and you can finish quickly on your laptop without taking too many computing resources, what we do is we work with a sort of toy model of a gravitational wave. So it's not sort of physical in any real sense. So let me give you a quick overview of this, and then I'll go on through. So this notebook, as usual, sort of set up at the start, but it has one additional feature that was actually added only in the last hour. So please pay attention just to this bit in case you're going to hit an issue. So there's this extra cell here, which is effectively downloading a file called toymodel.csv. And what that is it's a set of test data for you to analyze in this notebook. If you are using the notebooks on your own computer, then you will need to pull, do a git pull to get the latest version of that, or you can simply go to the GitHub page and just download it. What you'll find if you don't do this is later on you'll see some sort of complaint that this file doesn't exist. So if you just use Colab, then you'll be completely fine so as you loaded it in the last hour or so. And thanks very much to Anuj, who was the mentor which spotted this last night and gave us the fix. So yeah, a bit of a last minute coding in there. Okay, so with that resolved, so this just downloads that data file. There's some text here which is essentially telling you a little bit in more detail what Soichiro talked about, so that hopefully is going to be sort of useful to just read over. And then we introduce a sort of fake, if you like, signal. So this is, not real gravitational wave data. It's just faked with this sort of funny looking sine Gaussian signal in here. And then from this, it essentially proceeds to sort of describe the model that we're going to be using, and then goes on to how we do parameter estimation. So in this case, we have a model which includes a couple of parameters. They include things like the width of this signal, so it's a sort of pulse, and then also the frequency of that pulse. And the goal of this is really to show you how to do inference of this. Now, often parameter estimation is described as a black box, and you sort of throw your black box and get some posteriors, and we've seen examples of posteriors. Well, the hope with this notebook is to give you a peek inside of that black box of what's really going on. And so it introduces the idea of sampling and shows you how to do sampling, and then shows you sort of why that's going to be complicated and some of the difficulties with making it efficient. And then we finish up, so we go through sampling and then Markov chain Monte Carlo sampling, so it's a sort of improved version of the initial sampler. And then it goes on to use a package called Bilby, which is an LVK piece of software that we use for our gravitational wave posterior estimation, which includes many tricks to make the sampling much more efficient. And so you end up sort of being able to compare these three different methods in the end. So that notebook is going to have the sort of details, but it's none of the gravitational waves. So the next notebook, so tutorial 3.2, is then moving on to looking at a real gravitational wave event. And so I open this one here. So in this notebook, it's going to actually grab the data for GW150914, so our first binary black hole observation, and then it will walk you through some of the sort of technical details of gravitational wave parameter estimation. So sort of things like power spectral density estimation, things that you've sort of heard of before, and then how we construct likelihoods and some of the technical features of that. And the end result of this is being able to measure the Chirp mass and mass ratio for GW150914. Now, one of the things I want to highlight here is that if you want to do a sort of full parameter estimation for a binary black hole, it could typically take something like a day of computing on a single core laptop, much more if you want to use a very involved waveform. And so there's a number of different sort of tricks that have been done in this notebook to make it run in a few minutes. And so as a sort of, go through this today, but keep in mind that this is a rough and ready estimate. So you'll end up with something looking like this, so a measurement of the Chirp mass, which isn't too bad. But if you're going to sort of take this notebook and then, maybe you want to develop this into a project, do have a think about, what elements, what assumptions have been made to make it fast that you will need to go back and fix. So one of the tricks, for example, is we fix a number of the parameters. So that's in here. So we have a non-spinning black hole, for example. This essentially sets the spins of all the black holes to 0. And we know that binary black holes are certainly spinning to some extent. And so that's a bad assumption if you're going to sort of do astrophysics with this. If there's any sort of technical questions on that, please, of course, just put them in Ask.Igwin. Okay, and then the final notebook kind of looks at the outputs of parameter estimation. So this is discovering and using published posterior samples. So that's the end result of the inference process that Soichiro described. And this shows you how to download the data from the GWASP pages and then produce some plots from that. So for example, this is 150914 again. And has measurements. Sorry, it's not loading very well on my Cafe Wi-Fi here, but it sort of shows you the full measurements that you should be able to make. So that's a useful exercise if you want to sort of take tutorial 3.2 and then scale it up and see if you can reproduce 3.3. Quite a tough challenge, but one maybe for the future. And so I think that's all I wanted to say on those. And so please, do ask questions in Ask.Igwin. And I'll pass back to Agatha now.
Yes, thanks, Greg. Thanks for the introduction. And even if you were in a cafe, it was clear that's good. So, again, the last thing I want to say before ending all these things is, if you have been So I've been asked many times, and I repeat already, you can, I repeat again, you can go over the Thinkific website to do your exercise whenever you want, with your time, with your pace. There is no deadline to do anything. The only fake deadline I will just say now, and it's about the data challenge. So as you wait a moment, because I have to show the preview that you see, because that was my screen. So you see the workshop in this way. You see that you have seen that for each activity. For each tutorial, you have an activity, and we already told you you can submit your reply when you confirm you have the code that you should have done right, so that you have some guidance. And this is about all the tutorial in all the for all the activities. When you say activities for tutorial, blah blah blah, is always like that. Then this night we have added these 2 chapters to the Thinkific, and these are treated in a different way. So the data, what we call data challenge, is some kind of challenge that is in addition to the tutorial, to the exercises that are at the end of the tutorial. And if you go to this link, this should bring you to the README with all the explanation. So you will need to download these files, and then for those files you have some question you will be answered. You can follow the suggested things to do when you analyze each of these. So GWF is the format, the standard format, the gravitational wave file format that we use internally, but you have all the way to analyze it, and you see that there are points, because the idea is that you submit your solution in Thinkific, which means in year. But in this case, you see the aspect is different, because we don't give you options. We ask you just to put the number, and there are no suggestions, because the idea is that this part, what we call data challenge, this you should do on your own using what you have learned until now. So there are no suggestion in this case. And for this, we will have a look at all the answer, the solution that you put in. We give you 1 week to play with this. And in this, when we collect all the solution, then we will just check them, give points, and send an email to the winner. So it's a challenge in the sense that there is a winner, but it's a winner just for glory. Unfortunately, we don't have a prize, and in this online shared, gravitational shared diffuse workshop is hard to arrange more complex things than that. So we evaluate that solution that arrived until this day, but this does not mean that you should stop doing that after. You can play with this data and do your analysis when you want, so you can continue to challenge yourself. And then there is this other chapter that is called feedback, will bring you just to a survey, and it's the same link that I send all of the participants via email. And so please have a look at this survey. It's the question asked are mainly geographical. So the first 2 questions are just for statistics. So for us to understand which kind of audience we had and which was the geographical distribution. And then the other questions are more about how do you like the workshop and so on. If you please take your time to do that, even if it's just the first questions, because this would help us organize the next workshop. And I hope I said everything. I don't know if the others, Greg, Simone, Apratim, we want to add something else.
No, I think we are fine on my side.
Hi. So I just want to thank all the speakers, the mentors, and also my co-organizers for so that we could it's all, because of all of them, we could have this meeting, and also for the participants who joined. I just want to point out, though Agatha can mention the exact number, we had more than 1,500 applications. We had more than hundreds, we still have more than 100 of participants who joined us online. We have thousands of views already on YouTube. So I hope all of you learned a lot from this, from the lectures as well as the tutorials, and you will keep using the data available, and the public data which is available. And also just a reminder that if you want to join us online for the last day of the tutorials, we will again be back in half an hour from now. So, yeah.
Apologies, I just remember a thing just before we leave. I believe at some point we will provide you with the password to check for the solutions of the tutorials. And I think, Agatha, you will do it by email, right? We can email the password to the participants so that they can unpack the solutions for the tutorials.
Oh, okay, I don't know. Yes, we have to discuss that,
Yeah,
but in case the solution to the tutorial are inside the Thinkific already. So, okay.
Yeah, I mean, just to have the full solution at end.
Okay.
Okay.
Okay, so I guess that's it. We can close here. Again, if you have question, use ask.iguin.org. So thanks everybody, and bye. See you next time.
Goodbye. Thank you for joining us. Bye-bye.
Bye. I'll just go offline now.